at lunch to do your redo? Did we? I believe you. I thought it was today, but that's okay. Not gonna lose my mind over it. Don't lose yours. Okay, we're solving radical equations. We're gonna solve them algebraically. We're gonna talk about restrictions, because we never talk about restrictions. And when you did this in grade 11, so this is a grade 11 outcome, solving them algebraically. You guys did this in grade 11. But one of the things that you hated was restrictions. What did you guys tell me the radicand cannot be in a square root?
Negative.
Negative. You have no problem restricting it on a graph, but then when we get to this thing, it's like, I don't really want to deal with that. All you do for the restriction, you guys told me that the stuff under the root sign, which happens to be that, has to be a positive number, or what's the lowest value it can be? 0. So this has to be greater than or equal to 0. Everybody good with that? So x has to be greater than or equal to -5. That's your restriction, that's it. And all that's telling me is that if I get a value that is less than -5, it's not going to work. Because sometimes that happens when we square stuff. Do you guys remember what we called it? When you squared stuff and then you substitute it back in, it didn't work. Do you guys remember what we called it from grade 11? Yeah. Extraneous root? Does that ring a bell? No? Okay. All right. Just must have been me. Okay. So now that we've done the restriction, all my x values have to be greater than or equal to -5. Okay. That's giving me a solution range. So now let's go ahead. Grade 11, channel grade 11. What is the first step to solving this?
You make it x plus 5, where x plus 5 equals 3.
Okay. So you isolate the radical. Brilliant. So we just brought that 3 to the other side. What is the next step in solving an equation?
Square each side. Square
each side. Thomas, was this your favorite unit?
This is just like the easy unit.
Oh.
And then you just subtract the 5, so x equals 4.
X equals 4. Hey, does that fit into our solution set?
Yes.
Yes, it does. We're going to check it, though, just because we're smart people. You guys remember how to check your solutions?
Just do it.
Just do it. So you're going to substitute into the original. And when you're doing your check, you're looking for the positive principal root. So when we take that square root of 9, we're looking at the answer of 3. So that's a good answer. All right, I'm going to slide this up. We talked about this, systems versus zeros. So if we graph this as a single function, we are going to look for the zeros. What are the zeros? They're your x-intercepts. And you're like, Scallion, how the heck am I going to graph that table of values? How am I going to graph that table of values? Anybody? What? Properly. Okay, that's good. Yep, that's a solid plan. Do you guys remember that very first radical graph that we did? That most basic radical graph? Let's do it, that table of values. Remember we were purposeful with the x's that we picked? We picked 0, and if we took the square root of 0, it gave us 0. So this was the graph of that. And then what was my next value?
4.
Nope. 1. And then 4 and 2. And then what came after 4? 9. Right? That was our basic one. Easy peasy. Okay. That all passes. So this table of values, we're going to use these x values as a guide so that it helps us. No, we're not. We're going to do transformations. What's happening here with the transformations? Let's say it in words. If we're adding 5 to the x, which way are we going? Left. And then if we are minusing 3 outside, where are we going? 3 down. And if we were to put that into a mapping rule, okay, so let's do it transformation-wise. Okay. So 0, 0 transforms to?
-5, -3.
-5, -3. 1 transforms to -4. Maybe let's do all of our x's first. 4 transforms to -1. 9 transforms to 4. Now we're going to do the y's. So we're minusing 3 from the y. So that's going to be -2, -1, and 0. Everybody good with that? Let us graph it. I'm not going to graph the original graph. I'm just graphing the transformed one. So when we are asked to solve a function by graphing, it matters how we do it. I'm going to try to graph it with an erasable pen, but that hasn't been my best. Okay, and this point, remember, doesn't have an arrow on it. So this transform point will also not have an arrow on it. So we're going to be 5, -3. And then we're going to be -4, -2. And then -1 and -1. So a small bubble between the first two. And I'm going to have an arrow on that end. Ooh, that's probably my best radical graph yet. So looking at this graph, what's the solution? The only thing I care about, ladies and gentlemen, is the x. What's the solution? X equals 4, right? We're looking for the x-intercepts. So my solution so I don't want a coordinate pair, I want the x value of it. And when we solved it algebraically, what did we get? We also got 4. Okay. Now, this time we're going to graph a system. And so we're going to be looking for the points of intersection. We're going to break this into 2 equations. We are going to break this into 2 equations. We are going to break this into equation 1. That's equation 1. And equation 2. Is going to be where is going to be a positive 3. You're going to actually solve it. So equation 2 is going to be y equals 3. All right. Shall we graph the y equals 3 first? Okay, I see that you're all super excited for this. All right, so we're still going to do transformations on this one, and we're going to go back to this table, but the only thing we're transforming now is the x. So my first point is going to be 5, 0. My next point is going to be -4, 1. Because I'm not touching the y's, there's no longer a transformation with that y. So let's go ahead and graph that one. So 5, 0. Then we're going to have -4 and 1. Then we're going to have -1 and 2. And then +4 and 3. And again, that's my starting point. So I'm going to bubble through these two and then arrow on the right-hand side. I'm going to get another color, which I don't think will matter on this. And my handy dandy ruler, I'm going to graph the y equals 3. Oh, that should be a solid line with arrows going in both directions. I now have two graphs on the same coordinate plane. So this is y equals 3, and this guy is y equals root x plus 5. And when we talk about points of intersection, that's the point where the two graphs meet, where the two graphs touch. And where does that happen? Right there. And again, I don't care about the y coordinate. It's not a coordinate pair. The solution does not include the coordinate pair. It matters just the x. So the solution here is x equals 4. Everybody good with that? So again, the solution should be the same. We solved it algebraically and the answer was x4. We solved it graphically with one function and it was x equals 4, and we solved it with two functions, the system, and it was still x equals 4. So lots of ways to get it. I prefer to do algebra, but the grade 12 outcome is being able to graph and find the solution from the graph. All right. Okay, I'm moving my paper. Can you guys solve this guy? Can we do it algebraically? Step 1, isolate the radical. Oh, step 1, what's my step 1? Let's do a restriction. So the radicand has to be greater than or equal to 0. It's the same one. Okay, let's solve it. Thomas, I've isolated it. What's my next step?
Still just square both sides.
Square both sides, yeah. Okay, this is where people screw up. Welcome to grade 11 again. What is the most common mistake we make to do this? Yeah, like you treat them like they're not a thing. It really, what it means is you're multiplying the two binomials together. And in grade 11, if you were in my class, I made you write it out like that to remind you, and it still didn't help. But you're smarter people now, so I know that you're okay with this. If I have an x squared, what does that mean I need to do right away? I need to factor it or use my quadratic formula. I'm just not showing the steps. I hope you guys are okay with the math. So do you have the equal sign all the way down? Did you lose the equal sign anywhere? Do both of those satisfy the restriction?
Yeah.
Yeah? Okay. We're going to check our solutions. So we've got a 1 equals a -1. That doesn't help. So this one has to be rejected. I hope your grade 11 is flooding back. That you have to mark it off. You have to show that it's rejected. It's important to do the check, but you can't leave it at the check. You've got to go and reject that answer. Okay. All right. So for this one, how am I going to graph this? How am I going to graph this as a single function? As a single function, how am I going to graph this? I don't know. It's ugly. I don't wanna. So we're not going to do it this way. We're going to do it as a system way. So our first equation is going to be y equals x plus 5. And our second equation, because these are separated now, this is going to be y equals x plus 3. Okay, so we're looking for point of intersection. So now you see we're going to work smarter. We're going to do the points of intersection because it's really easy to graph a linear and then a one transformation radical graph. That's not too terrible, hopefully. So let's get to graphing.
Do we have to graph it? Or can we do it option?
Pardon it?
Do we have to graph it?
Do you have to graph it?
Like on lessons?
Yes. The grade 12 outcome is solving these things graphically. Algebraically was your grade 11 outcome. So the exact, so what you're going to see is it's going to ask you to graph it.
What's an outcome?
So the outcomes are the things that the province tells me I have to teach you guys. So the province dictates for every course in Manitoba that there's some sort of plan. Like, hey, in grade 11 pre-cal, you're going to learn these things. In grade 12 pre-cal, you're going to learn those things. Just like in grade 11 English, you're going to learn these things. Grade 9 English. All right. So this was 5, 0, 4, 1. Where's my other? I'm like, where's my table of values? I just graphed this one. -1 and 2. And then 4 and 3. And again, a bubble between the first 2 points. And an arrow out there, so that's my y equals root x plus 5. Now I'm going to do my linear graph. You guys are good at graphing these. 3, and then my slope is 1, 1, so I'm going to go up 1, over 1. Up 1, over 1. You're like, Sky, and that's not helpful. That's nowhere near it. So now I'm going to do the opposite. I'm going to go down 1 and left 1. Oh, look at that. Down 1, left 1. Down 1, left 1. So now I have my linear equation on here. Arrows on both ends of the linear. And the point of intersection. So the solution is x equals -1. Because remember, I only want the x value. Because the y value will change whether I'm using zeros or points of intersection. How do you guys feel about that? Good? It's not too terrible, but you see the value of using the intersection points instead of the zeros. As soon as you get that extra x in there that's not under a root sign, it kind of messes everything up. Oh, guys, I did this using technology. I don't think we're gonna do this question. Because I did it with technology and it was really ugly.
Actually, this doesn't look that bad because you can just get it to like the x squared. It's easy to like use like quadratic formula on this. Is what I'm saying.
You can totally use quadratic formula, but how would you solve it graphically?
That's a much better question, I guess.
Right? Like, I'm all fine for the algebraic, like that's all good. But I think graphically, this one's not very nice. So we're not gonna touch this one. We're gonna skip this. How nice is that? We're gonna skip it, and it's only 2 p.m. and I'm skipping things. Do you guys wanna solve it algebraically? No? It was gonna be such a good time though. Okay, super easy with radical word problems. They're probably gonna give you the radical and you're just gonna work with it. And this is again, like kind of a grade 11 outcome where you're just pulling out the important information and you're gonna solve it algebraically. Engineer designs a roller coaster, involves a vertical drop section just below the top of the ride. She uses the equation V equals V initial squared plus 2AD. V velocity in feet per second, D is distance in feet, V initial, and A is constant acceleration. The design specifies that the speed of the car's ride must be 120 feet per second at the bottom of the vertical drop section. Why would that be? Why does it have to hit a certain speed? Anybody? Why does it have to hit a certain speed? Has anybody been on a roller coaster?
Oh, to satisfy the riders.
To satisfy the riders, absolutely. You want their stomachs in their chest. But you need to have enough momentum to get through the next up part, right? So you're coming down, you need to have enough momentum to get to the up part. Do you guys know? Physics, people, physics. We need to travel through. If the initial velocity of the coaster on the top of the drop is 10 feet per second, and the only acceleration is due to gravity, 32 feet per second squared, what's the vertical drop distance that should be used to the nearest foot? What am I solving for? What am I solving for? Vertical drop distance. D. I'm solving for the letter D. So what is the initial? If the initial velocity of the coaster is 10 feet per second, what's initial velocity? 10. Okay, good job. What must my velocity be at the end of that drop section? 120. So I guess how well can you work with fun stuff like this? Gravity was 32. And D we're trying to find. I'm just going to do that. I like to do the stuff under the root sign, just because it makes it a little bit easier. Thomas,
What?
my radical is isolated. What's my next step?
Just square both sides.
Square both sides. What's 120 squared? It's got a 144 in it.
14,400.
Nice. Says to the nearest foot. You guys can't see that. Bless you. And that's it. That is it. Solving graphically involves graphing. Shocker.